So, molecular spectroscopy is nothing but it is a study of how molecules interact with the electromagnetic radiation. So, interaction of the molecules with electromagnetic radiation, it is going to mainly it is going to be how. Okay. So, interaction of interaction with the electromagnetic radiation. Interaction with the electromagnetic radiation. Right. So it refers to study of how molecules interact with the electromagnetic radiation. So mainly in the molecular spectroscopy, it involves the what we call absorption, emission, or scattering of light by molecules to gain the information about their internal structure. Okay, to know the internal structure, otherwise physical phenomenon or chemical phenomenon, what it is happening. To know about that one, this molecular spectroscopy is very important. It's very important to know that interaction, like analysis of absorption, emission, or scattering of light to know the information about the structure and energy levels. All these, if you want to know, this molecular spectroscopy is very important. So in the case of this, it is going to be involve different regions of the electromagnetic spectrum. So different regions means like it is going to be involve ultraviolet, visible, as well as the infrared and the microwave. All these regions, it is going to be involved here. Okay, different regions of electromagnetic spectrum, such as what we call the first UV, that is ultraviolet region, as well as the visible region, as well as the what we call we have like a IR region, which we are calling it as a infrared region. It is going to be involved, and as well as the microwave region, the electromagnetic spectrum. All these regions, it is going to be interact. Okay, different regions of the electromagnetic spectrum, like UV, visible, IR, and microwave regions are used in various types of molecular spectroscopy we are going to be using. So mainly the molecular spectroscopy is nothing but it is going to be study how the molecules interact with the electromagnetic radiation. Okay, how the molecules will interact with the electromagnetic radiation. So in this interaction, we involve like analysis of absorption, emission, or scattering of light by molecules to know the information about their structures as well as the energy levels and different things we can know whenever this electromagnetic radiation is interacting, right? So that is what we have the molecular spectroscopy definition we have. So if you see the different types of molecular spectroscopies, if you see, different types of molecular spectroscopies also we are going to see. So here is what we have. So interaction of the electromagnetic radiation is what we call it as a molecular spectroscopy we are going to be called. So as I told that different regions of electromagnetic spectrum, we have like a ultraviolet region, infrared region, and microwave region, which we can have to study about this molecular spectroscopy. So now we'll see the next one. That is, we have like, as I told that basing upon so we have like different types of molecular spectroscopies we have. So mainly we can see the different types of molecular spectroscopies or T types we have mainly. Broadly, if you see the division of this molecular spectroscopy is into three types we have, like electronic spectra we have, vibrational rotational spectra we have, and similarly we have this what we call a pure rotational spectra we have. So mainly broadly it can be divided into uh, what we call three types of molecular spectra we have. So when light from what we call light from a source containing substance in molecules, when light from a source containing in a what we call containing a substance in a molecular state is sent into a spectrophotometer. So more or less what we call broad wavelength regions are observed in the spectrum. So when a light from a source containing a substance in molecular state is sent into a spectrometer, more or less broad wavelength are observed in the spectrum. So these regions we are going to be call it as what bands we are going to be called. So these regions we will be calling it as what bands we are going to be called, and the spectrum is called it as a band spectrum we are going to be called. It is going to be called it as what band spectrum. That is nothing but whenever the light source containing some substances or molecular state is sent to a spectrophotometer, you are going to be observe these bands, and this spectrum we are going to call it as a band spectrum we are going to be call. Otherwise, we will be calling it as a same. We will be calling it as a molecular spectrum. Also, we are going to be called. We will be calling it as what molecular spectrum. Also, we are going to be called here. So as I told that this molecular spectrum mainly can be divided into three spectral regions. It can be divided into three spectral regions. What are those spectral regions which we have here is three types of we are going to be see here. So these are going to be divided into three different types of spectral regions divided, different types of transitions between the molecular energy states it is going to take place. So the first one which we have is mainly like what we call electronic spectra is there. So we have electronic spectra. So what is electronic spectra? We'll see in detail. So then we have like another one, vibrational and rotational spectra. Vibrational and rotational spectra is there. And a third type of the spectra which we have is a pure rotational spectra. Okay, pure rotational spectra is there. So these are three spectra which we have broadly divided this molecular spectroscopy. So in the case of this first one, if you take this, which we are going to be call it as electronic spectra. So this electronic spectra are observed both in the case of the emission as well as the what we call absorption. In the case of emission as well as the absorption, these can be observed. And this both emission and absorption in the visible and ultraviolet region we are going to be seeing. Okay, the spectra are observed both in the case of the emission as well as the absorption, and these electronic spectra is going to be observed in the visible as well as the ultraviolet region. So this electronic spectra are going to be observed in the visible region and as well as the what. Next we have another one, that region is UV region. In both these regions, this electronic spectra can be observed here. So this electronic spectrum, if you take, so this electronic spectrum consisting of a what we call a quite large number of bands it is going to be have. It is going to be consisting of a quite large number of bands it is going to be consisting. And each individual band if you take, so each individual band is having a sharp edge. Okay, it is each individual band is having a sharp edge, which we will be calling it as a band head we are going to be called here. Okay, each individual band is going to be have a sharp edge, which we are going to be call it as a band head we are going to be called. So where the intensity is suddenly falls to zero here, where the intensity suddenly falls to zero. And from this edge, the intensity falls off gradually to the other side of the band. Okay. So if you observe this electronic spectra, if you observe what we call under a high resolution, if you see, so a band is found to be composed of series of lines which draw like there is nothing but actually we are going to be observe one thick band. You are going to be observe this one. So this band you are going to be observed. So this, if you observe in a high resolution spectrophotometer, if you observe, so this band is found to be composed of a series of lines which draw further apart as the distance from the band head increases. Like that is nothing but it is again divided into in the this is going to be like a, it can be observed in the vertical in the sharp resolution spectrophotometer. If you see this main band, it is going to be again divided into these three types. That means it if you observe this band, you can able to see three different or two different bands you are going to be see here. So this is what we have, the electronic spectra we have. Okay, and this band, whichever you are going to be observed, this band is said to be degraded towards the side opposite to the band head, towards the opposite to the band head it is going to be have. So these electronic spectra are observed for the what we call mainly in the case of the heteronuclear as well as for the homonuclear diatomic molecules. Okay, so this electronic spectra can be observed in the both the cases of heteronuclear as well as the homonuclear uh, uh, you are going to observe homonuclear diatomic molecules you are going to be observed. So what is heteronuclear and homonuclear means? Suppose if you take the homonuclear, so we will be having like a similar same uh, we have like a H2. If you take, this is the example of what we call homonuclear molecule we have. And in the case, suppose if you take N2 or O2, like this, if you take different molecules, we will be calling it as a homonuclear molecules we are going to become. And whereas in the case of the heteronuclear molecules is nothing but the two atoms are different. You are going to be have two different atoms. It is going to be form it as a molecules. Then the type of molecule we'll be calling it as a heteronuclear molecule we are going to be called. So suppose if you take the example of what we call a heteronuclear molecule, if you take, so this heteronuclear molecules examples like we have HCl is one of the example for heteronuclear molecules we have, and CO, otherwise CN, and so on. Like this, we have different molecules we have. So in the case of the heteronuclear molecules, two different atoms are formed as a heteronuclear molecules, whereas in the case of the homonuclear molecule, two similar atoms are going to be formed as a homonuclear molecule. Example for heteronucleus is heteronucleus is HCl or CO and so on, and for homonuclear, it is example is H2, N2, O2 you are going to be have. So these are homonuclear molecules. So that means this electronic spectra can be observed. This electronic spectra can be observed in the case of the what we call both the homonuclear as well as the heteronucleus. So in these two cases, it is going to be observed, both in the case of the heteronucleus as well as the in the case of the homonuclear molecules, you are going to be observe this electronic spectrum. So in the case of the electronic spectrum, what it is happening means it can be observed in the case of emission as well as the absorption in the visible as well as the ultraviolet region. It can be observed, and as well as we can say that this single band whichever we have. So this single band whichever we have, this is going to be observed it is divided into some other bands if you observe in a high resolution spectrophotometer. So this is about electronic spectra which we have. So next we will move to another type of spectra which we have is what we call a vibrational rotation spectra. So these spectra, molecular spectra, broadly it is divided into three types: electronic spectra, and as well as this what we call uh, vibrational rotation spectra, and we have pure rotational spectra. Next, we will discuss about what we call this one, that is a vibrational rotational spectra. Okay. Next, we will discuss about vibrational rotational spectra. Okay. So this one we are going to be discussed. Vibrational rotational spectra we are going to be discussing. So in the case of the vibrational rotational spectra, so this spectra, vibrational or rotational spectra is going to be observed in the case of the absorption. In the case of the absorption, it is going to be observed, and that too, it is going to be observed in the near infrared region. In the case of the near infrared region, we can observe. So near infrared region means it is going to be have around 1 micrometer to 10 to the power of 2 micrometers. Okay, it can be observed in the near infrared region, that is 1 micrometer to 10 to the power of 2 micrometers, it is going to be observed. And in this vibrational rotational spectra, each spectrum, it is consisting of intense band, okay, intense band, called it as a fundamental band, we are going to be called. So, which is accompanied by some few weak bands, it is going to be. Okay, in the case of the vibrational rotational spectra, it is going to be observed in the absorption, you are going to be observed in the near infrared region, that is around 1 micrometer to 10 to the power of 2 micrometers, it is going to be have. And in this case, each spectrum consisting of intense band, which is calling it as a fundamental bands, we are going to be called, which is accompanied by what we call weak bands, it is going to be have. So these bands, like electronic bands, have a fine structure. Fine structure means, again, it is going to be divided into 3 different uh, levels, it is going to be divided. Okay. And if you take this vibrational rotational spectra, so this vibrational rotation spectra can be observed in the case of only in the case of the heteromolecular, otherwise heteronuclear molecules. Heteronuclear molecules. Only in the case of the heteronuclear molecules, it is going to be observed. Whereas in the case of the homo nuclear molecules, this vibrational rotational spectra does not produce. In the case of the homonuclear molecules, like homonuclear molecules means we have given like examples, hydrogen, what we call nitrogen, oxygen. In these cases, this vibrational rotation spectra is not going to be observed. Mainly this vibrational rotational spectra is going to be observed in the case of the only hetero nuclear molecules, it is going to be observed here. So this is about vibrational rotational spectra which we have. Next, we'll move to another type of molecular spectra we have, that is pure rotational spectra, which is a pure rotational spectra here. So we'll discuss about this pure rotational spectra. So next type of one we have is a pure rotational spectra. Pure rotational spectra here. So in the case of this pure rotational spectra, so this spectra is going to be observed in absorption only. This pure rotational spectra is observed in the case of the absorption. And the region where we are going to be observed is in the, we will be having what we call far infrared region. Is going to be observed in the far infrared region. The far infrared region. So generally the far infrared region is nothing but it is going to be have the range like 10 to the power of 2 micrometers to 10 to the power of 3 micrometers. It is going to be observed in the case of the far infrared region. And also it is observed in the microwave region also. It is observed in the microwave region also. It is going to be observed here. It is observed in the microwave region. So the microwave region is nothing but it is in between 10 to the power of 3 micrometers to 10 to the power of 4 micrometers. So in between 10 to the power of 3 to 4 micrometers, it is going to be observed here. So pure rotational spectra is going to be observed in the far infrared region, 10 to the power of 2 micrometers to 10 to the power of 3 micrometers, and the microwave region, that is 10 to the power of 3 micrometers to 10 to the power of 4 micrometers region, it is going to be observed here. And again, if you take pure rotational spectra, like each spectrum, if you take, so this each spectrum is composed of a series of nearly equidistant lines it is going to be have. Okay. The spectrum is composed of a series of nearly equidistant lines it is going to be have. Nearly equidistant lines. Equidistance lines it is going to be have. Okay. So like vibrational rotational spectra, the pure rotational spectra is also observed in the case of what we call heteronuclear diatomic molecule. So this is also is going to be observed in the case of the heteronuclear what we call diatomic molecules only. It is going to be observed here. Okay. So these are 3 types broadly it has been defined here. So if you see in depth the classification of these what we call this molecular spectra here we'll see. So here in depth, if you see, again, what types of molecular spectra which we have here. So here we see different types of molecular spectra again here. So we will be having like a UV visible spectroscopy. So as already we have discussed. So in the case of the UV visible spectroscopy, the absorption of UV or visible light is going to be takes place by the molecules. So in this case, electronic structure, if you see, so that can be occurred, the transition can be occurred between the electronic energy levels. Between the electronic energy levels, the transition can be occurred. So if you see the application of this, what we call this UV visible spectroscopy, here we can see the application like studying conjugate systems and concentration measurement in solutions. In the case of the, if you want to measure the concentration measurement of the solution, this UV visible spectroscopy you can have here. So next type of spectroscopy which we have here is infrared spectroscopy. And already we have seen in infrared spectroscopy, vibrational rotational spectra you are going to be get here. So here you see, already we have discussed like this is going to be observed. Okay, so in the case of the vibrational transitions, this vibrational rotational spectra we can call. So this infrared spectroscopy in this under, we are going to be study this vibrational rotation spectra. And why we'll use this vibrational rotation spectra means to identify the functional groups of the molecular structure. In depth, if you see why we use this vibrational rotation spectra, the vibration spectra is to study the functional groups of the molecular structure we'll be using. And generally, this will be used in organic chemistry. Okay, so this is so next we'll move to another type of spectroscopy. So infrared spectroscopy, we have like a nuclear magnetic spectroscopy we have. So in the case of the nuclear magnetic spectroscopy, absorption of radio frequency radiation, you are going to get in the what we call by nuclei in a magnetic field. So under the magnetic field, you are going to be see this one. And we have mass spectroscopy, and we have another type of spectroscopy also is there. That is mass spectroscopy. So which is measures the what we call charge ratios of ions for molecular weight determination. So these are different types of molecular spectroscopies which we have. So next, we will move to actually what we call that is rotational spectroscopy. So because you people, you have rotational spectroscopy is there. So we will move to what is rotational spectroscopy here. Right. So what is rotational spectroscopy here we see in depth about rotational spectroscopy we are going to be studying. Rotational spectroscopy. Otherwise, pure rotational spectra. We are going to be study about rotational spectra. What is actually this is like is a pure rotational spectra actually. Okay. We are going to be study about the pure rotational spectra here. So if you see what is pure rotational spectra, so pure rotational spectra, that is we will be calling it as a pure rotational molecular spectra we are going to be called. So this pure rotational molecular spectra, it is going to be arises, otherwise why we are getting this pure rotational spectra means it is going to be arises uh, from the transitions between rotational energy states. Okay, pure rotational molecular spectra arises from transition between what we call the transitions between what we call rotational energy states, between the rotational energy states, in the rotational energy states. Okay, so pure rotational molecular spectra arises from the transition between the rotational energy states. It is going to be observed, and it is going to be observed in the region of the electromagnetic spectrum is it is going to be observed in the far infrared region. It is going to be observed in the far infrared region. The far infrared region, it is going to be observed. The far infrared region is nothing but it is going to be in between 10 to the power of 2 micrometers to 10 to the power of 3 micrometers. In this region, it is going to be observed, and as well as the, or in the case of the microwave region, in the case of the microwave region, case of the microwave region, as discussed, microwave region is in between 10 to the power of 3 micrometers to 10 to the power of 4 micrometers. So in between these electromagnetic spectrum, this pure rotational spectra is going to be observed here. And this pure rotational spectra is going to be observed in the case of the molecules which are having what we call a permanent electric dipole moments. Okay, so the molecules that have permanent electric dipole moments can absorb or emit electromagnetic radiations. So the molecules which are having what we call a permanent electric dipole moments. Permanent electric dipole moments can absorb or emit electromagnetic radiation, which we will be known as like a transitions. Okay, so only molecules that have permanent electric dipole moments can absorb or emit electromagnetic radiations in such transitions. Okay, so that means like if you take any what we call nuclear diatomic molecules, if you take in the case of the homonuclear diatomic molecules, whichever we have seen, like in the case of the H2, O2, or N2, or whichever we are going to be have. So in the case of these homonuclear diatomic molecules, what we call and symmetrical molecules like CO2, whichever we are going to be take. So in this case, this rotational spectra is not going to be observed. In the case of the homonuclear diatomic molecules, and as well as in the case of the what we call symmetric linear molecules, examples like a CO2 if you take, because CO2 is nothing but a O double bond C, this what we call O you are going to be have. So in this case, as well as the what we call spherical top polyatomic molecules like a CH4 or whatever we are going to be take, in all these cases, this pure rotational what we call spectra, it is not going to be observed, because mainly the rotational spectra is going to be observed in the case of the permanent electric dipole moment can absorb or emit electromagnetic radiations in the form of a what we call transitions. It is going to be observed here. So mainly the rotational spectra is going to be observed in the case of the heteronuclear molecules only. That is what we have to remember. So now if you take this right. So now if you take this spectra, this spectra is observed in the case of the absorption for heteronuclear diatomic molecules. Like examples for heteronuclear diatomic molecules, if you take, we have like what we call HCl. In the case of the HCl, we can observe. In the case of the HF, we can observe. Otherwise, HBr or otherwise CO, or so many heteronuclear molecules will be there. In these cases, it is observed here. Okay. So the rotational spectra It is consisting of actually simple series of absorptions, maxima, which are very nearly equidistant. Okay, so the rotational spectra consisting of a simple series of absorption maxima, which are very nearly equidistant on a wave number scale. So if you see what we call this one, so here in this form, it is going to be observed here. So the maximas, whichever we are having. So these are equidistances you are going to be have. So like this, the spectra, this, okay, like this you are going to be observed. So if you observe the figure of this equidistant on a wave number, so the maxima's absorption of the maxima, they are going to be very nearly equidistant on a wave number scale you are going to be have. So wave number scale means like it is going to be have a new centimeter inverse. Okay, centimeter inverse. So in this form, it is going to be observed here. Okay, equidistance maximas you are going to be observed here. So the measurement of frequencies of these maximas, the measurement of frequencies of these maximas leads to determination of what we call moment of inertia and the internuclear distance of the molecule. Okay, so if you measure the frequencies of these maximas, if you measure, then it is going to determine the what we call moment of inertia. Is going to be determined the moment of inertia. It can be determined and as well as the internuclear distance of the molecule. Internuclear distance, internuclear distance of the molecules. Okay, internuclear distance of the molecules also it can be measured. So for homonuclear molecules which do not give rotational spectra, the moment of inertia and the internuclear distance can be found from the rotational fine structure of the electronic bands and from the rotational Raman spectra. So that is different thing. That is, if you want to find out in the case of the what we call homonuclear molecules, if you want to find out the moment of inertia as well as the internuclear distance of the molecules, if you want to find out, then you have to go for what we call rotational Raman spectra you have to take. Then we can see the internuclear distance of the molecules as well as the moment of inertia of the molecules you can be find out. So this is what some features of the rotational spectra we have. And suppose if you want to get this rotational spectra, what are the requirements which we have to be? What are the requirements which we have to see here? So the requirements of rotational spectra we'll see here. See the so here see molecular requirements. Molecular requirements. Molecular requirements for rotational spectrum. For rotational spectrum. What are the molecular requirements for the rotational spectra? We'll see here. Right. So the basic requirements for this emission or absorption of radiation, the basic requirement for the emission or absorption of radiation by transition between what we call rotational energy states is that the molecule must have permanent dipole moment. So mainly the required thing is first it should have the permanent dipole moment. So if we don't have the permanent dipole moment, then we don't observe the rotational spectra. Okay. So first one which we have is the molecule should have the permanent dipole moment. So if you take the classical mechanics, classical electrodynamics, if you take, according to which rotating molecule can lead to emission of radiation, which provides a changing dipole moment which is associated with the molecule. So all these heteromolecules, hetero means heteronuclear molecule, heteronuclear diatomic molecules with unlike atoms, means two different atoms you are going to be have, for which the centers of positive and negative charges do not coincides, which are having the permanent dipole moment. So if you, in the case of the only heteronuclear molecules which are having two different atoms you are going to be have, okay, we have the two different atoms we are going to be have. So in that case only we are going to be get this what we call a rotational spectra you are going to be have, right? So in this case, during the rotation of the molecule, so during the rotation of the molecule, the component of the dipole moment, in a fixed direction changes. Okay. In the case of the what rotation of the molecule, the component of the dipole moment in a fixed direction changes periodically. Okay, with frequency of rotation. So frequency of rotation means we will represent with the new rotation. New rotation we can call. Okay, so whenever it is rotated, classically, whenever it is rotated, the molecule, whenever it is rotated, classically the radiation of frequency should be emitted. So whenever it is rotated, it is going to be emitted certain radiation, which is new radiation it should be have. That means the frequency of radiation should be emitted. So in the case of the homonuclear molecules, they have no dipole moment, and hence there is no emission of infrared radiation is going to be takes place. And in the case of these heteronuclear molecules only, as they are going to be rotated, so whenever they are rotating, so they are going to be emit certain radiation, and that radiation is going to be having certain frequency, which we will be calling it as a new, we will be calling new rotation. We are going to be called here. Similarly, in the infrared radiation can be absorbed by the rotating molecules. Okay. Similarly, the infrared radiation can be absorbed by the rotating molecules and thereby increase the rotation. One thing is, whenever the molecule is rotating here, they are going to be, whenever they are going to be rotating, they are going to be emit certain radiation, with certain frequency, which we are going to be call it as a frequency as new rotation of we are going to be call. Suppose similarly, it is going to be take the infrared radiation. That means by absorbing this infrared radiation, as we told that rotational spectra is going to be absorbing the infrared radiation as well as the microwave radiation. So by absorbing this infrared radiation, so it can be rotate the molecule. It can be rotate the molecule and thereby increases the rotation. So in this case, whenever the molecule is rotating, it is going to be emit certain radiation of the frequency new rotation we are going to be called. And similarly, by taking certain infrared radiation, that means by absorbing certain infrared radiation, the molecule is going to be rotates. That means it is going to be increases its rotation. Okay. So only if a permanent dipole is present. So in these two cases, we have to think that there should be a permanent dipole, then only these two things going to be happen. That means it is going to be by rotating this, it is going to be emit certain radiation of frequency, new rotation we will be calling. Otherwise, if it is present a permanent dipole moment, by taking this infrared radiation absorption, it is going to be emit certain what call sorry, it is by absorbing the infrared radiation, it is going to be rotate its molecule. That is by increase this increases the rotation of this molecule. Okay, that is in the case of the only heteronucleus molecules because they possess the permanent dipole moment. So when such a molecule interact with the oscillating electric field of the incident radiation to absorb the rotational energy and produces the absorption spectrum here, will be by taking what we call the infrared radiation. And that means it is interacting with the oscillating electric field of the incident radiation to absorb the rotational energy and produces the absorption spectra here. Okay. So here, if you take how this is going to be happen, that means the rotation of these molecules, how it is going to be happen. So for any instant, the molecule is in such a position that the electric field pushes the positive charge up and the negative charge down. So here, if you see how it is going to be takes place. So here, sure. Okay. So here the positive charge up and the negative charge down. Electric field pushes the positive charge up and the what we call a negative charge down. So here if you have a positive charge, okay, positive charge, so which is rotating, it is going to be pushes upwards, and at the same time, negative charge if you take, so this rotation is going to be pushes downwards here. Okay, so the electric field pushes the positive charge up and as well as the negative charge down. So as in this manner. Okay, so which makes the molecules rotates here, which makes the molecule rotates, and as the electric field is absorbed by that molecule, what we call the rotation is going to be makes faster. So now suppose if a frequency of radiation consisting with that of the nuclear with that of the molecular rotation, then half cycle you are going to get half cycle. That means next cycle will be in this manner. So in this. So here this is a negatively charged will be in the upward direction. Positively charged is going to be in the downward direction. Okay. So if frequency of radiation coincides with that of the molecular rotation, then half cycle this you are going to get. The electric field would be what we call still make the molecule rotate faster, which makes by pushing the what we call higher rotational energy and producing a rotational spectrum. Thus, the production of the absorption spectrum is due to the electric dipole moment of the molecule here. Electric dipole moment of the molecule. So homonuclear molecules have no dipole moment, and hence there is no absorption in what we call in the infrared radiation. So as we discussed, homonuclear molecules they can be have, but in the different spectra, that is a rotational Raman spectra, which where we can observe here in the case of the homo nuclear molecules. So here in the case of the what we call the molecules which are having the permanent dipole moment in the infrared region or what we call microwave region, we are going to be observe this one. So this is how the rotational spectra is going to be takes place and the requirements of the rotational spectra which we have. Okay. So next we will move to the molecule as a rigid rotator. Next, we'll see the molecule as a rigid rotator. The molecule as a rigid rotator. Molecule as a rigid rotator, we'll see here. So this will explains the rotational spectra here. So here, this is the simplest model of a rotating diatomic molecule is that of a rigid rotator. So the internuclear separation is assumed to be fixed at the equilibrium value. So here what we'll do is we will be considering two atoms. We are going to be consider two atoms which are having like a mass M1 and mass M2. Okay, we are going to be consider two atoms of masses M1 and M2. So which are chemically bonded to form the diatomic molecule here. Okay. Suppose here if you see how these are there, molecules have the so here we will take one molecule which is called it as a M1, another molecule which is M2. They are separated by certain distance. Okay. So suppose this is rotating in this fashion. In this fashion. So center here will be, we have this center. Okay. So here the distance between this center to the first atom which is having mass M1 is will be taken as R1, and similarly the distance from the center to the second one which is R2. Okay, and the total distance from here to here is I take it as a R. Take it as R here. So this is what we have the axis of rotation. Axis of rotation. We have the axis of rotation. So this is going to be rotating in this direction. Okay, this is going to be rotated in this direction. Right. Now we'll see here. So we have considered that two atoms of masses M1 and M2, which are chemically bonded to form a diatomic molecule. So the atoms may be treated as a point masses. These atoms M1 and M2 may be treated as a point masses because their masses are concentrated in their nuclei, which are having the size of very smaller in size, around 10 to the power of minus 15 you have. Okay, it's much smaller than the internuclear separation. Okay, so here R, whichever we have taken, R be the distance between these two atoms from first atom to second atom. The distance is R we have taken, and the distance between the what we call atoms M1 and M2 is R we have taken, and R1 is there and R2 is there. R1 and R2 are the distances of the atoms from the molecular center of mass we have. Okay, so this system is capable of rotation about an axis. This system is capable of rotating about this axis. Okay, about this axis, which is passing through the center of mass, which we call it as a C. C is perpendicular to the internuclear axis. C is perpendicular to the internuclear axis we have. So now here we'll see by the definition of the what we call by the definition of the center of mass, we have like a M1 R1 is equals to M2 R2. By the definition of the center of mass, we have M1 R1 is equals to R2. And moreover, we know that R1 plus R2 is equals to R we have. Okay, moreover, we have R1 plus R2 is equals to, we have R. Okay, and from that we can find out the value of R1 as well as the R2 we can find out. So what is the value of R1 and R2 we can find it. So from this equation, what we have is from this equation, we can write what is that R1, we can write it as what M2 R2 by M1 we can write. M2 by M1 R2 we can write. So therefore, we can write this as M2 by M1 into R2 value. From this equation, we can write it as what R minus R1. So here if I substitute, we can get R minus R1. So we have got R1 is equals to M2 by M1 into R minus R1. So this again we can write as R1 is R1 into 1 plus M2 by M1, which is equals to M2 by M1 into R we can write. Okay. So therefore, R1 we can write it as, if you take this side, it will be M2 by M1 plus M2 into R we can write. So we are going to get what we call R1 is equals to M2 into M1 plus M2 into R you are going to get. Similarly, the value of R2 also we can get. So similarly, we can write here we are not. Similarly, the value of R2 also we can write. So R2, what we calculate is, we get R2 as R2 is equals to, like we are going to get it as a M1 by M1 plus M2 into R you are going to get. So we have got the value of R1 is equals to M2 by M1 plus M2 into R. And similarly, we have got the value of R2, that is the distance from the center to the second atom M2 is M1 by M1 plus M2 into R you are going to get. Okay. So this is what we have get the R1 and R2 value. Now the moment of inertia of the molecule about the axis of rotation. As it is rotating around this axis of rotation, we can get the moment of inertia of the molecules about the axis of rotation. So that can be written as I is equals to what we call M1 R1 square plus M2 R2 square you have. Okay, I is equals to M1 R1 square plus M2 R2 square we have. So here in this, if you substitute R1 value, if we substitute, we are going to get it as what we call M1 into R1 value is what we have, M2 by, right, M2 by M1 plus M2 square plus, here I put different color, right. So plus here we have like a M2 into R2 value is M1 by M1 plus M2 whole square. Okay. So I is equals to M1 R1 square. In this place R1 we have substituted M2 by M1 plus M2 whole square plus in place of M2 into R2 place we have substituted M1 by M1 plus 2 whole square. So by combining these two, the moment of inertia of the molecule, okay, the moment of inertia of the molecule I is equals to, we will be getting it as M1 M2 by, if we solve this equation, we are going to get it as M1 M2 by M1 plus M2 into R square we can get. I is equals to moment of inertia, we are getting it as what? M1 M2 by M1 plus M2 R square we are going to get here. So this M1 M2 by M1 plus M2, we will be calling it as a reduced mass. We'll be calling it as what? Reduced mass. M1 M2 by M1 plus M2, we'll be calling it as reduced mass. Generally, we'll represent this reduced mass with mu we are going to be represent. So therefore, we can write this moment of inertia of the molecule about the rotation of the about what we call about the axis of rotation. We are going to get it as I is equals to mu R square we are going to get. Understand? I is equals to mu R square we are going to be get here. So that is by taking mu as a reduced mass we are going to get. So that the diatomic molecule is equivalent to a single point mass we are going to be get here. Okay. So this system we will be calling it as what a rigid rotator we are going to be called here. So here after this, this solution, whichever the rotation, whichever we have got, the rotation of the diatom molecules is equivalent to a single particle mass, which rotates about the axis of the distance, which is located at this what we call distance of r we have. So this treatment, whichever we have treated, like I is equals to mu r square, whichever we have got. So this we have got with the help of what we call classical mechanics. So according to this, all energies of rotation are possible. All energies of rotations are possible according to the classical mechanics. Whereas if you take the quantum mechanics, however, in the case of the quantum mechanics, so according to the quantum mechanics, it will tells that it will having what called certain discrete rotational energies are possible. It is having only discrete rotational energies are possible. So in other words, the rotational energies are quantized, we can say that according to the quantum mechanics. Now, by taking the quantum mechanics into the account, we will be taking, we'll be solving what we call the frequency of rotation we are going to be get here. The energy, first we'll get the energy of rotation we are going to be get here. So now we'll see that one. Right. So according to the quantum mechanics, the angular momentum of the particle is m is equals to I omega. The angular momentum of the particle is m is equals to I omega. So where omega is nothing but omega is a angular frequency. Omega is, we call it as omega is nothing but it is a angular frequency because it is rotating around this axis. Omega is angular frequency we have. So according to the quantum mechanics, the angular momentum of a single atom can be written as PL, which is equals to root of L into L plus 1 into H by 2 pi we can write. So this is the vertical according to the quantum mechanics, the angular momentum of this single atom. We can write it as what PL is equals to root over L into L plus 1 H by 2 pi we can write here. So where this L is nothing but that is the orbital quantum number. It is L is nothing but orbital quantum number we can call orbital quantum number. So it can takes the values like L value can be taken as 0, 1, 2, and so on we can write here. Therefore, for a diatomic molecule, the angular momentum is, for the diatomic molecule, the angular momentum is m is equals to root over j into j plus 1 into h by 2 pi. The particular, for the diatomic molecule, the angular momentum is m is equals to root over j into j plus 1 into h by 2 pi, and j is nothing but the rotational quantum number here. J is nothing but the rotational quantum number we can have, and j can takes the values like from 0, 1, and 2, 3, and so on. It can take here. J can take the value of this all like a 0, 1, 2, 3, whatever it is going to be have, it is going to be taken here. And according to the classical theory of energy rotation, which we can write it as a energy of rotation as a EJ, we can write EJ, we can write of a rigid rotator. So which we can write it as a EJ is equals to half I omega square, we can write half I omega square, we can write here. Therefore, EJ is equals to, we can get it as a half into I into omega value. In place of omega, we can write it as a m by I whole square. M by I whole square. M by I whole square we can write here. So since we know that m value is equals to, we have this as since m value which is equals to m square value, if you take, it is equals to j into j plus 1 into h by 2 pi whole square means h by 4 pi square we have. Okay, h square by 4 pi square. M square is equals to j into j plus 1 into h square by 4 pi square. So therefore, if you substitute in this m value in the above equation, if you substitute, you'll be getting it as EJ is equals to you are going to get it as what? Half into, okay, half into, you are going to get it as I into I square is there. So we are going to get it as j into j plus 1, j into j plus 1 into h square by 4 pi square. I will get cancels. Here you'll get 1 by 2 I you are going to get. So therefore, EJ value, finally we are going to get it as what? H square by 8 pi square I is there into j plus 1 we are going to get. Okay. So this is the what we call it is the EJ value which we are going to get. EJ value we are getting it as what? H square by 8 pi square, 8 pi square I into j plus 1 you are going to get here. So here j is nothing but the positive integer we have here in this case. Okay. If the transformation is occurring uh, between the two levels, like this is about EJ we have got. Next we will take right. So if you right. So if you take if the transformation is occurring between the levels, the transformation is occurring between the levels j plus 1 level to j plus 1 level to j level. Okay, if the transformation is occurring between the levels j plus 1 to j energy level, if it is occurring, so the energy difference we will be calling it as what? Delta EJ we are going to be calling. Okay, so if the transformation occurs between the j plus 1 level to j level, then the energy difference we will be representing with the delta EJ. So this delta EJ is generally equals to h nu. E is equals to h nu. So this delta EJ is equals to h nu you are going to be having. So delta EJ is nothing but energy transferring between the levels j plus 1 to j. So it is EJ plus 1 minus EJ, which will be equals to this h nu. So this value actually, this value will be equals to, okay. So it is in between the two levels as we have got EJ value like h square by 8 pi square I we have got. So that is h square by 8 pi square I, and it is in between the level j plus 1 to j level. So it will be, if you substitute there, it will be j plus 1 into j plus 2 minus j into j plus 1, j plus 1. Okay. So if you solve this entire value, we are going to get it as h square by 4 pi square I, h square by 4 pi square I into j plus 1. Okay. So this is what we are going to get. So, and we have said that this energy difference is equals to h nu. So this entire value should be equals to h nu you have to get. So therefore, if you find out nu, the frequency of rotation, we are going to get it as a, if you solve this one, you are going to get it as h by 4 pi I, okay, h by 4 pi I into j plus 1 you are going, into j plus 1 you are going to get. So the new value, you are going to get it as what? H by 4 pi, 4 pi, 4 pi square, sorry, is 4 pi square, 4 pi square I into j plus mu you are going to get here. So this is the, in what we call the molecule as a rigid rotator. So in this, what we have considered is we have considered that two atoms of having the masses M1 and M2. The masses are having M1 and M2. So which are separated by certain distance R, and the distance from the center of the what we call axis is R1 we have taken, and from the mass M1 to atom of the mass M1 to center is R1, and another atom having the mass M2 to the center is R2 we have taken. Okay. So then we have considered that the moment of inertia we have taken. Otherwise, from the definition of the center of mass, we have taken M1 R1 is equals to M2 R2 we have got. M2 R2 we have got. M2 R2, and then we have taken R1 plus R2 is equals to R, and we have solved the R1 value. R1 is equals to, we have got M2 by M1 plus M2 into R we have got, and similarly R2 value we have got it as M1 by M1 plus M2 into R we have got. And from the moment of inertia of the molecule, about the axis of rotation is given by I is equals to mr square, as we have like a two masses of atoms M1 and M2 we have, that we have got it as I is equals to M1 R1 square plus M2 R2 square, which we have. Okay. I is equals to M1 R1 square plus M2 R2 square we have got. So from that we have got the reduced mass equation as I is equals to mu R square we have got. Reduced mass equation I is equals to mu R square we have got. Okay. And mu is nothing but reduced mass as M1 M2 by M1 plus M2 we have got. Okay. M1 M2 by M1 plus M2 we have got. So the rotation of the diatomic molecule is equivalent to a single particle of mass which rotates about an axis which is located at a distance of r. So far that I is equals to mu r square, whichever we have got, that is the treatment which is involved the classical mechanics. So according to this classical mechanics, all energies of rotations are possible. So whereas in the case of the quantum mechanics, if you consider, the quantum mechanics will tell us that only certain discrete energy levels are possible. So in other words, we can say that the rotational energies are quantized, we can say that. So by taking the quantum mechanics into account, so the angular momentum of the particle, we can write it as a m is equals to I omega we have written. So where omega is nothing but the angular frequency we have called, and we have written the what we call uh, uh, angular momentum of a single atom as PL is equals to root over L into L plus 1 h by 2 pi. Here L is nothing but the orbital quantum number, which can take the values like 0, 1, 2, 3, it can take for a diatomic molecule. And similarly, for a diatomic molecule, the angular momentum can be written as m is equals to root over j into j plus 1 into h by 2 pi we can write. Here j is nothing but the rotational quantum number. Again, it can take the values like 0, 1, 2, and so on. It can be taken. So, and we can write what we call, according to the classical theory of energy of rotation, Ej can be written as a half j half I omega square, not j omega square. Ej is equals to half I omega square we can write. So therefore, we can write Ej is equals to half I omega square, and omega is nothing but angular frequency. We can substitute omega is equals to m by I here. So from this equation, so half into I into mi whole square, m by I whole square we have written, and m square we can write here. Already we have like m value is root over j into j plus 1 into h by 2 pi is there. So therefore m square we can write it as a j into j plus 1 from this equation. So from this equation, from this to this, if you write m square is equals to j into j plus 1 by h square by 4 pi square. So therefore in this, if you substitute, Ej is equals to half into j plus 1 by I into h square by 4 pi square you are going to get. Overall, we are going to get it as Ej is equals to h square by 8 pi square I into j plus 1 we are going to get here. Okay. So this is the energy of rotation Ej of a rigid rotator we are getting here. Okay. So now if you consider that the transformation occurs between the what we call levels like a j plus 1 level to j level, if it is occurring, And then the energy difference, we can write it as a delta Ej is equals to h nu, we can write. Delta Ej is equals to h nu, we can write. So therefore, here we take a delta Ej is nothing but from j plus 1 level to j, that is Ej plus 1 minus Ej is equals to h nu, we can write. And this Ej plus 1 minus Ej is equals to this value already, because Ej value we have got. So that we have written as this entire value we have written. So from that, we have got a new value is equals to h by 4 pi square I into j plus 1. That is what we have got here. So this is about the molecule as a rigid rotator we have. So new rotation, this frequency of rotation is h square by h by 4 pi square into j plus 1 we have got here. So this is the what the rigid rotator. Now we'll see the rotational spectra and observed rotational spectra and energy levels we'll see here. Okay, what are the observed spectra? That is observed rotational spectra. So next we'll see the observed rotational spectra. Observed rotational spectra and energy levels. Energy levels. Right. So the exactly observed spectrum is very low energy range you have in this case. So here, in order to see the observed rotational spectra and different energy levels, so we'll investigate the spectrum expected from a rigid rotator. So in terms of wave number, the energy equation here we can write it as f of j. The energy equation can be written as f of j, which will be equals to E by hc. So which is equals to, we can write it as a h by already, which we have derived 8 pi square IC, okay, into j plus 1, we can write. Okay. So now we will take this h by 8 pi square IC, whichever we have, we will be considering it as a b here, we will consider. So therefore, we write that as a b. So we are going to get it as, we are writing it as h by 8 pi square IC is equals to b, which is called it as a rotational constant, which is called it as what? Rotational constant we are going to get. So therefore, we can write f of j is equals to, now what we can write? F of j is equals to b into j plus 1, we can write here. Okay. B is equals to j into j plus 1, we can write here. And now here, j values, it can take like a 0, 1, 2, and so on, you can take here. So if you substitute the j values 0, 1, 2, 3 in this equation, if you substitute, so this f of j, you are going to get it as, okay, the energy equation, you are going to get it as like f of j is equals to, if you substitute 0, you are going to get it as a 0. If you substitute 1, you are going to get it as a 2b, you are going to get. To substitute 2, you are going to get it as 6b. Next, continuing, you will getting 12b, next 20b, like that you are going to get, and so many. So thus, we have a series of discrete energy levels, discrete rotational energy levels, which are having space is increasing by j here. Okay. So here in this case, if you see the rotational energy levels, if we draw how we are going to get this is like uh, when initially when J is equals to 0, you are going to get it as a J value here will substitute. J is equals to 0. This f of J value again it is going to get 0. When J is equals to 0, f of J is equals to 0 you are going to get. And when we take J value is equals to 1, when we take J value is equals to 1, this f of J value is going to get it as what? 2b you are going to get. F of J is equals to, you are going to get it as 2b. And when we take this J value is equals to 2, this f of b value is going to get it as what? 6b you are going to get. That means the distance it is increasing. And when we take this 3, you take this J value is 3, you are going to get it as a 12b you are going to get. And when we take this 4, you are going to get it as a 20b you are going to get. You take this 4. And likewise, you are going to get different values you are going to get. So this is 0 to 1 level we have. Okay. This is from 2 to 6, that is 1 to 2. And next we have 2 to 3. Next we have from 3 to 4 here. Okay. So like 2b, this is next, it is how much? The difference is 4b. Next, it is how much difference? 6b, it will be there. Next one will be 8b, we have. Okay, 8b. And so on. Next, you'll get difference is 10b, you are going to get. Next, if you take j is equals to 5 here. So I'll do this one. Right. So in this case, when we take this j is equals to 5, if you take, so you are going to get this as a 30b you are going to get. So therefore, it will be 10b here. So actually, the distance you can see in this manner also. It is 2b, then we have 4b, again 6b, then we have 8b, then 10b we have. Okay. So the transition takes place between an upper j and lower j. The wave number of the emitted absorption can be taken as what we call nu. Nu is equals to the reference. Nu is equals to the, suppose if you, the transition is taking place between two different levels, like suppose one is a j dash, another one is a j double dash. If you take the absorption of radiation, which is having a wave number. Okay, the wave number of the emitted or absorption radiation given by nu is equals to f of j dash minus f of j double dash. That is in between two different energy levels we have. So if you write in terms of B, if you write, it will be B into j dash into j dash plus 1 you have, minus it will be B into j dash j double dash into j double dash plus 1 we are going to be have. Okay. So like this what we have is j changes by unity only, like j can be according to the selection rule, delta j is equals to plus or minus 1 only we are going to be have. Okay, delta j is equals to plus or minus only you have. So like this, the frequency of rotation nu is equals to, you are going to get 2b, 4b, 6b, and so on. You are going to be get here. So the constant b is obtained by knowing b. We can evaluate the internuclear distance between the atoms by determining the moment of inertia. So by determining the moment of inertia, we can determine what we call the internuclear distance between the atoms we can determine. So this is what the observed rotation spectra and different energy levels we have. Okay. Next, we'll see the isotopic effect of rotational spectra. Isotopic effect of rotational spectra. Isotope effect of rotational spectra. Isotope effect of rotational spectrum. So the reduced mass, we have represented mu in this case for rigid rotator. The reduced mass is mu, and hence the rotational constant also we have got, which B is equals to, which we have got like a h by what we call 8 pi square mu r square c. Okay, h by uh, mu r square c we have got. So the reduced mass mu, and hence the rotational constant B is equal to this we have got is different for different isotopic molecules. The reduced mass and as well as this what we call the rotational constant B is different for different isotopic molecules. So since the mass effects are negligible compared to the electronic effects in the determination of the equilibrium internuclear separations, the separation is the same in two isotopic molecules, only reduced masses are going to be different here. So if you take B dash is the rotational constant for the heavier isotope, suppose we take B dash is the rotational constant for the heavier isotope, then we have like B dash will be less than B you are going to be have. And similarly, we will be having what we call F dash J uh, is less than F of J you are going to be have here. Okay, it is going to be have less than F of J. Okay, so therefore, as the separation levels for the heavier isotope will be smaller than those of the corresponding to the levels of the lighter isotope. So generally, if you see the isotopic effect, so in this manner you are going to be have. So for two different one. So this is for Fj. And if you compare the F dash J, it is going to be less than that smaller you are going to be. So this is another one level. Take another energy level. So it will be in this manner you are going to be. So for different values of J here, I'm drawing. So I'll put those values of J here. Almost same. So this is for J is equals to 0, and this is for J is equals to 1, and this is for J is equals to 2, and this is for J is equals to 3, and this is for J is equals to 4. So for different values of J, F of J value will be this you have, and F dash J value will be this you have. Okay. So these are the isotopic effect of rotational spectra. These are the isotopic effect of rotational spectra you have. So these are the generally as we seen that the separation levels for the heavier isotope will be smaller than those of the corresponding levels of the lighter isotopes. Okay. Hence the spectral lengths will be also very closer here as we have seen. So this is of isotope effect of vertical rotational spectra we have. So this is about the molecular spectroscopy, in which we have seen the rotational spectra, that is unit 11, which we have rotational spectra of the diatomic molecules. So first we have seen the molecule as a rigid rotator, in which we have considered the two atoms of masses M1 and M2, which are separated by certain distance R we have taken. R1 is the distance between the first atom, and R2 is the second distance we have. From that, we have calculated the what we call rotation of energy EJ value we have calculated, and from that we have calculated the new rotation, the frequency of radiation we have calculated, and also we have seen the observed rotational spectra of energy levels we have seen. Okay. The isotopic effect of rotational energy levels is this one. Okay.